You may have learned from physics that if an object is thrown in a field like this, it will describe a parabola. But what will be the shape of the path if the object was thrown in a field like this? Will it describe a spiral? An ellipse? Will it ever reach the center? Let's first remember how you solve these kind of problems. We're given some initial velocity, and we know that the acceleration is the second derivative of the position with respect to time. Now, this acceleration is equal to the field's acceleration acting on the object, which in these cases is usually gravity. That is, g pointing downward. With the initial height, we can easily find the object's position as a function of time by integrating twice. From this, it can be deduced that the trajectory will be parabolic. Let's now analyze our problem. It's clear that here, to express position in space, it's much more convenient to work with radius and angle, like this. Now, in this kind of fields, acceleration is inversely proportional to the square of the radius and points toward the center. Knowing that the object is launched from a certain radius capital R, and simplifying this equation slightly, using prime notation, we are ready to solve the problem. It is important to keep in mind that r and theta are functions of time. Let's focus on the left-hand side of the equation. Do you remember the square of a sum? Well, there is a similar formula for the second derivative of a product. Let's use it. We now continue expanding the expression. We distribute, rearrange, and group. Now this has to be equal to minus k over r squared times the vector with components sine theta and cosine theta, which is like also having this other vector multiplied by 0. This leads us to a system of two equations. Taking the second equation and multiplying it by r, we find that r squared times theta prime is always the same. This has to do with the conservation of angular momentum. So, r squared times theta prime is always the same. Then it will also be at the beginning. We know initial radius, capital R, and initial angle, 0. But be careful, we don't know initial theta prime. What we know is that initial velocity is v pointing to the right. Now we know that velocity is the first derivative of the position with respect to time, which we can express in our terms as follows. Working with the initial conditions, we arrive at the conclusion that initial theta prime is v over capital R, and also that initial r prime is equal to 0. We substitute, and it follows that r squared times theta prime is capital R times v. With the first equation, things start to get interesting. We multiply by minus 1 and r squared. We apply what we found before, divide by that, and with this magic trick, we have gotten rid of time. Now it is possible to know the shape of the path because we know how r and theta relate to each other. Note that we can solve the equation for 1 over r. Here's the solution. Those two constants are missing. Now, if you remember that initial r prime is 0, and you have a good eye, you can find the values of a and b. Now we can solve for the radius, simplify, and at last we have obtained the trajectory function, and it looks like this. If v is equal to 0, if we increase the velocity, an elliptical path will begin to form. Note that the body returns to its initial position. If the body is launched with sufficient velocity, it will orbit around the center in uniform circular motion. This concept was already present in Newton's Principia. That velocity is equal to this value, and it's also known as first cosmic velocity or orbital speed. We continue increasing the velocity, and we find that the path becomes elliptical again. If the speed is exactly the square root of 2 times the orbital velocity, the body will no longer return to its starting point, and it will describe a parabolic path. This velocity is also known as second cosmic velocity or escape speed. And as you might have guessed, if the speed is even greater, the trajectory will be a hyperbola. We now have a general idea of how the object moves, and this seems to apply to planets and other celestial bodies. Interestingly, this is also how an electron would move if it were launched in an electric field generated by a large positive charge. Let's go one step further and figure out how the object moves as a function of time. In other words, let's figure out what the video of the moving body would look like. Well, here we are again. So this time we'll be working with Cartesian coordinates, keeping in mind that r is equal to the magnitude of the position vector and, of course, that x and y are functions of time. Separately, these are the coordinates of the acceleration, which we'll multiply by the corresponding coordinates of the velocity. Now we add them, multiply by dt, and see what happens in a certain time interval. It turns out that on the left we find the magnitude of the velocity, and on the right, again, the magnitude of the position vector. Let's take time 1 as the start, and time 2 as any later time. The rearranged equation reminds us of the law of conservation of energy. So, it's very easy to know the magnitude of the velocity, but not its components. The cool thing about this is that it also works in 3 dimensions. Let's continue. We multiply by 2, isolate the velocity squared, rewrite it our way, remember the expression for velocity and r times v, and with a few more steps we obtain the following equation. Now it's not difficult to solve for t. We call everything on the right-hand side f, and t turns out to be this. Everything that appears here are things we can know, and it has this shape. This is t as a function of r. To find r as a function of t, we have to flip the graph like this. Now we need to complete the graph symmetrically to satisfy the equation we saw before. We now know r as a function of time. We can now solve for theta by isolating it from the trajectory equation we obtained earlier. If the function is cyclic, meaning the trajectory is elliptical, it's possible to find the period using the previous time function, which will give us the semi-period. We will find not only pi, but also this other thing, which turns out to be not the smallest distance, not the greatest distance, but the average distance of these last two, that is, the semi-major axis of the ellipse, which we will call A. If we arrange the equation in a nicer way, we will find that the period squared divided by the cube of the semi-major axis is constant. We will find Kepler's third law. Having done all that, we finally can plug r and theta into the position vector.